Hello and welcome to The Interface, the Hindus podcast to make sense of the accelerating pace of change underpinned by technology. I'm your host, Sean Xavier. AI, as you know, is in the news every other day, and there's a lot of development around AI with new language models that are coming up. But what's the history behind all this and all that's happening in AI? Where did they all start from? And how do you decode AI's rich history? That's what we're going to explore today in our podcast. I'm joined by Shreya Subramanian, Principal Data Scientist at AWS. Dr. Shreyas contributes to cutting edge research in deep learning, foundation models, and optimization techniques. In his current role at Amazon, he's working with various science leaders and research teams within and outside Amazon, helping to guide customers to best leverage state of the art algorithms and technique. Shreyas, welcome to the interface.
Thanks, John. Pleasure to be here, and thanks for having me on and letting me share some thoughts that I have. Like you said, every day we have changes that we're seeing, and it's tough for even us to keep up with the pace. Literally, there are tens of thousands of papers, technical papers being published every year, so it's kind of impossible to even keep up with that, even though this is our day job. So yeah, happy to dig into. It's sometimes important to pause and see where we've come from, and it's interesting to know that a lot of the underpinnings of what we have today was established even 50, 60 years ago. So happy to dive in.
Right, great. Yeah, like I think even before this podcast could start, you were discussing earlier. I'd like to, start the whole discussion from the backdrop of, let's say, the neural nets and maybe connecting that to the AlexNet framework. If you could give a brief history about those times and how the technology was developing and what kind of algorithms were kind of going into building those systems. That'd be a great starting point, I guess. Would you like to take it from there?
Yeah, happy to. I think this goes way back even before our Indian independence. I think there's a couple of papers that folks started off with in terms of really simple models of artificial neurons. And the purpose of those neurons really was to, compute some very simple logical functions, right? And we see that today in like the design of, semiconductors and transistors and things like that. But, think of these compute units that can pretty much, output a 0 or 1, based on some input. So very simple. And, back in I think the 50s, Rosenblatt developed this model called the perceptron, which is still used today. I mean, it's used today in large language models in some way because it has dense layers. It's used in adapters to make these large language models more efficient. So it's it's surprising, but also it's these are some of these fundamental works that have stood the test of time. And these perceptrons really are simple. Pattern recognition kind of compute units. And the idea of perceptrons are to, have universal function approximators, which means, the aim is I can translate any input to any output, right? And of course, that's a really lofty goal. You can't, imagine all the kinds of inputs that are possible as audio and video and image and text and tables. And today we're not even touching the surface of any to any kind of foundation models. But back then, that was kind of the motivation. And these perceptrons really showed that these single layer neurons could solve problems like the XOR function, right? So it's like super simple logical functions. And at the time, neural networks really was not a cool thing to be doing. There was not really a lot of interest in this. Most, researchers did, this is up to, I think, 70s and beyond, like, not really too much interest in this. And statistics and core mathematics and physics really was flourishing in terms of like research. And this whole learned functions was kind of mostly ignored. And early 2000s really is when we see neural networks coming back and then used in pattern recognition and different types of mappings. And I think this is still a good framework to, I think, keep in mind to understand, right? So you can go from any kind of input to any kind of output, um, today as well, when it comes to foundation models. And that's the aim with AGI and all of these other concepts, is to kind of understand the mode of input to interpret what the user is asking as output, and translate that through a learned kind of mapping, right?
In the mid 2000, I mean, roughly if we take that particular time, how
Yeah,
did these neural nets, the not exactly an explosion, but gradually it was starting to take a little more shape and form. Could you give a sense of, how that was happening around that time, leading to the AlexNet?
right. Yeah. So like I was saying, this is, early 2000s is when really it became cool again to work on neural networks. But then the hardware hadn't, caught up with the science yet. So it was kind of impractical to do things that we're doing today with GPUs and specialized compute units for certain types of models. So earlier it was really low power and low capacity hardware units, and limited in terms of amount of data as well. And so the real renaissance period started with the introduction of deep learning techniques by Jeff Hinton and others, right? And in parallel, there was also development of the early, graphics processing units, which were not meant for this, but it's a great application, and even more, I guess, a common application today of GPUs. And that coincided with massive data sets of like that are curated by humans, essentially, loads and loads of human curated data that actually came up with I guess ideas around how to train these models efficiently. And that AlexNet was one of the first models, and is really popularized by winning this ImageNet competition. So ImageNet is a huge database of images, and the goal is to translate that into categories, right? So you could have an airplane, you could have a motorcycle, you could have an animal, you could have a fruit. And these are kind of arbitrary if you think about it, and it's still going on. Like a lot of papers are still published with ImageNet as the base, but it came back in, AlexNet set the baseline by basically saying, you've been doing deep learning for some time right now as a field. And this was basically, we talked about perceptrons earlier. If you combine these perceptrons in, a stack, and let's call that one layer, and then you connect the outputs of that layer to another layer, which is another stack of perceptrons. That's a fully connected deep learning network. And that has, even that is useful for, classifying images in the case of ImageNet. But, AlexNet introduced this deep convolutional neural networks. The only change they made in this entire picture of, a stack of neurons connected to one another is the kind of neuron, right? And a nice way to kind of imagine this is like, imagine you have a printout of a picture on your table, right? And you had one of those pieces of colored plastic, it's maybe the size of your thumb, right? And you moved that colored plastic across the entire image, and you saw kind of something that's different, right? So you see a filtered version. And that's what they call a kernel in CNN, or convolutional neural network literature. And the operation that we're doing is basically called convolution. And the goal of a convolution neural network, unlike a traditional deep learning or fully connected perceptron network, is, can you guess the weights of those filters, right? So imagine in that case of the red filter paper or plastic that you are running across this printout of an image, maybe it's composed of three blocks. That's one is slightly more red, one is slightly less red, and one is completely transparent, right? And those are, imagine those are kind of weights that you have to train on, or you have to figure out. And what we see is the traditional, optimization literature coming to the rescue here. And I have a bias because I have a background in optimization as well. And so what we see here is like, algorithms like backpropagation, which is basically kind of applied chain rule to figure out based on, here's the input, I'm going to try this out, and here's the output. You measure the error in the output because you know that this particular picture is an airplane, and it's not something else this network guessed it as, and that's kind of an error signal. You use that error signal to adjust the weights of many of these filtered, plastic little sheets. At the end of which, if you train it long enough, you should see that this, when we say a model is trained, basically now you have a collection of, different colored filter papers that are kind of frozen in time now, and that's your model. And you have to apply it in a particular way to go from picture to a class, right? So that was kind of a really interesting, very different architecture. And we very rarely see these kind of differences. CNNs still exist, and many in production products are made of CNN. But I'll pause there. I think that's a great, kind of turning point when we talk about AlexNet and ImageNet. ImageNet is also one of the first large scale, like well curated data sets that everyone could go and try out their algorithms on.
Right. It's interesting. I mean, that's a very interesting way to kind of help visualize the whole CNN's architecture. This was also the time when a lot of experimentation was happening with the recurrent neural networks, which is another area. Could you kind of give a distinction between the two, the RNN and the CNN?
Yeah. So, when we talked about things like a piece of text or an image, you kind of think of it as stuck in time. So this doesn't have a time component to it. It's not a video, it's not audio, which is kind of pieces of sound bits across time. It's not a time series. So these algorithms we talked about traditionally were not good at the sequential data or handling sequential data. And what we started to realize is basically everything we see is a time series. It's a time series of text, time series of speech bytes, time series of just numbers for forecasting. And in order to do well at these time series data, and it doesn't have to be time, by the way, it can be just a series of or sequential series of data, right? And the missing component from the earlier CNN literature is you have to be able to form some sort of a memory, right? So imagine you're forecasting the weather in your city. I'm from Bangalore, and I remember when it was more pleasant, and now I've heard people complain about traffic and also about weather. So, but imagine you're forecasting, just the weather. You have access to the last months of weather data, and ignore that you have, seasons and other things like that. But you just have to figure out based on the last 30 days of data, figure out what the temperature is likely going to be on the next day, right? So all the things we spoke about right now, deep learning networks, which are just multi-layered perceptron kind of networks, also CNNs, typically you would have to treat that entire month's worth of temperature data or weather data as a snapshot, as a picture of the airplane or a picture of which turns out also works, but that came as a realization later. But the core idea behind RNNs is when you're processing the sequence of data, this network or this the network has to learn to deal with both the current input, which is, let's say, January 30th worth of weather, as well as everything from Jan 1st to Jan 30th. And this helps it basically, weight different factors, weight different, portions or days or months or weeks, and maybe this is a weekend. All these factors are learned, and then you do a prediction of what it's going to be on Feb 1st, for example. And what they realized is this was great in terms of, I mean, logically it makes sense and it's still being used, right? So what they realized is there's a fundamental, kind of deficiency with RNNs, which is we spoke a little bit about back propagation and base and optimization, finding weights and all of that. The real signal you get while doing this training. So, you'll see in recent research reports, you'll see here's this model that's been trained for one epoch or 10 epochs, right? What that really means is you start off with the data set. Every time you go through the entire data set, it's one epoch and you keep counting, right? So you might go, let's say you have 10,000 records. You might process 10 records at a time, which is called a batch. And you do that 1,000 times to go through your entire data set, which means you have done one epoch and 10 epochs of that. And this learning is progressive. And the signal you get basically from that error signal that we talked about earlier is called a gradient, which is again back to optimization. It's, I'm not going to change my weights and parameters randomly to find the best answer. I'm going to use this information about the error and the gradient to find the direction in which to change, which is the still currently the only way you can train models. I mean, there are some kind of obscure pieces of literature where you don't have to do gradients, but predominantly like any model that you and I have been using daily for, everything from, summarizing to generating emails are all based on back propagation gradients, right? So back to RNNs, what they realize is this significant problem called vanishing gradient. And and this really comes into play when trying to learn long-term dependencies, right? So now bring in like seasonality and now bring in other things that affect the weather that kind of you can't predict. And you'll see kind of because of this vanishing gradient, the training can become very unstable and there's no change in the model, basically rendering this learning very ineffective. So it's like trying to remember a very long sequence, and then by the time you reach the end, the kind of the connection to all of the previous data points that you saw is very weak, and so it's kind of no point, and you kind of output something that's a random weather. Which, by the way, if you ask a large language model today that hallucinates, what is the weather in Bangalore, it'll confidently say it's whatever 27 degrees. So we're getting better at that. But but this used to be a really a bit significant problem, which would leads to better sophisticated architectures, short-term memory, LSTM architectures, and gated recurrent units, which are all kind of slightly different variations of recurrent neural networks. And they introduce some special kind of constraints to basically to control what information to remember. So there's a separate memory module, what to forget, and what to pass along to the next LSTM unit or next neural unit. So, and in terms of a timeline where we're basically at 2015, let's say. So that's not too far back.
And if you want to, I mean, just to get an analogy for the human and the machine here, to see, where these architectures got their inspiration from, it's largely from the human brain. So, could you give a sense on, how the literature from the human brain mapping and understanding the connections in different neurons in the brain, how it is affecting the way computer scientists are taking that to make machines learn. Could you speak about that angle?
Oh yeah, definitely. I think this is a extremely interesting field, especially to myself. I like to think if I wasn't doing this, I would have been doing something related to neuroscience,
Brain research.
for sure. But I don't like the entire feeling of cutting into a skull and a brain. So that's why I'm here doing theoretical stuff. But there's a lot of research that's been done on the neuroscience side, which hasn't yet translated to foundation models, machine learning models, which is what the surprising thing is. If you go back to once again, like many decades ago, everyone's heard of Pavlov's associative learning, which basically led to
Mm.
reinforcement learning and all of that. Which is, for
Correct.
folks who are listening, it's the dog and the bell experiment, right? And that was way back. And what we saw, zooming to today, we still don't understand enough about the brain. Certainly not a human brain. We have done, as I guess, as a species, we know a little bit more about smaller brains, maybe mice brains, maybe even smaller, fruit flies and things like that. But one thing is for sure, basically evolved to do, or the brain is basically evolved to do things that we can't do effectively even today after so much, like billions of dollars of funding and the smartest people on it. Which is, to just name a few things, think of a kid basically looking at an orange, or maybe looking at two oranges, and then for the rest of his or her life, he or she knows basically what this object is. Which, if you have to train a model to do it, even today, maybe 1% of the time, the best models will say this is an apple and not an orange. So it's kind of disappointing. But this is called like very few shot learning, right? Meaning one
Yeah.
example. One example of a bicycle is enough to kind of know what a
Right.
bicycle. And then, basically we see that, in terms of the number of, relating it back to foundation models of today, we saw, DeepSeek, that's 670 billion parameters. Llama is 405
Yeah.
billion parameters. Our brain really is made up of a trillion cells, which you can't map to parameters really. But 90% of these are not neurons. It's only 100 billion neurons, and 90% are called glial cells. So the strange thing
Sorry,
is,
what
like,
cell is that?
it's called
Glial, is it?
glial cells. It's kind of a glue. It's kind of matter that connects all these cells, and there's definitely a function to it. But
Mm.
if you count up just the neurons, there's only 100 billion neurons, which, today's large language models, which are very, very limited, exceed
Have
those.
even more parameters. Yeah.
Yeah, exceed those numbers. And uh, what really maps to, our weights that we learn inside those neurons is these connections. And so neurons in our brain have these dendrites, and each neuron might have thousands of dendrites. And this maps to multiple parameters in a neural network. And
Mm.
we all kind of know that our foundation models are over parameterized, which means there's more capacity in those models, and we just haven't reached kind of saturation yet. Our brains are super efficient at doing all kinds of sensory information in parallel. So you could be looking at a plate of food and smelling it at the same time, and then you get kind of a output reaction to it. Um,
Mm.
and that's still not efficiently done. I mean, right now we kind of have a Frankenstein of different kinds of networks really that do these separately, and we try to merge them together really, even in today's
Right.
and these large language models are fixed. Ours are not. Our brains are not fixed. You can have some parts of it that are long term memory, some parts of it that are changing in time. So there's so many architectural, I guess, should I call it choices, or just evolved parts of the design that we still don't understand in terms of, what is, we talk about pruning today in our foundation model literature, which is kind of making the model more efficient. You kind of reduce the flow, the type of the data, and you reduce the number of connections. And this is all kind of an artificial way to mimic what is naturally happening in not just human brain, but any brain pretty much. And yeah, a lot more to talk about. But even simple things like, we talked about back propagation and the way of learning, which we know is a very, very inefficient way to learn, right? So you have to pass in a batch of data, which sometimes today you can't even go, higher than a single record, right? So in terms of large language models, that single record could be a tokenized piece of text. And that's all you can afford to do, because the rest of it is hogging the GPU memory. and
Right.
it's super inefficient. You go through a forward pass, which takes some time, and you measure all of the errors and the final error, and you do back propagation all through the network in the reverse area, and then you get all the gradients, and then you have to make a step towards the next, iteration of the model, and you're still very far away from the output. Versus it's still a kind of a mystery how the brain is able to do all of these things super efficiently, and there's no real, it's kind of an energy minimization task now, right? So you can't spend so much energy similar to what we're doing with back propagation in today's models. So there is no real, I mean, it's still, there's a lot of theory behind this, but there is no real answer about how it actually learns and how
Right.
it's retaining memory and how it's kind of changing and augmenting data. And we've heard of, we've seen in many movies, right? So if you some people kind of associate colors with music, some others will associate
Hmm.
tastes with with the look of a food, and it's kind of a
Right.
complex being. So we're very
Yeah.
very far off, and sometimes I feel like I want to take a peek into the future to see where where this is going, because right now the more I get into neuroscience, I feel like we're just kind of playing around. We're not really there yet. I mean, we're kind of this is the opposite end of the spectrum of all the people who believe, oh, this is the time to be alive, and billions of dollars going in AI. Whereas I feel we're walking around with something much more powerful. Yeah.
Right. Yeah. I mean, to kind of, give a little more shape to the idea that you described. Would it be fine to say that in terms of evolution, the human brain has come like eons, I mean, come to a very different place and time. While if you want to look at machine brain, let's say whatever machine learning task you're giving to different other language models or whatever, it's still in a stone age sort of an environment, and a lot more has to be done to develop it to get it to a particular stage when we want to really call it an intelligent system which mimics the brain. Would it be fair to say
I think
in
so.
terms
I
of
think so.
current research?
I wish more kind of cross pollination would happen between neuroscience and this AI literature, and it goes into everything, right? So it goes into hardware design, algorithm design. When it comes to hardware design, for example, the brain uses like few watts of, it's like a bulb, really, in terms of the amount of power that it uses. So remarkably, efficient compared to, we're talking about all these big sustainability programs and
And it doesn't use fossil fuel.
exactly, exactly. So like a single, one of the most popular GPUs today is the A100 GPU, right? And that's a single GPU, meaning no one uses a single GPU today. It's usually a cluster of thousands of GPUs, but a single GPU
Right.
can consume 500 watts, versus all your entire brain is doing 20 watts. Um, and I used to be, for a short period of time, my master's thesis was on analyzing dragonfly flight maneuvers. Dragonflies basically are the most, if you look at it, it's super small. I mean, everyone's seen a dragonfly, very small. So head is even smaller, which means brain is even smaller. But
Right.
dragonflies have evolved to be basically the best hunters in the highest success rate in hunting, 90 something percent, better than any other animal that exists today. And
Wow.
it's like super
I didn't know that.
efficient. And there's our research back then was, can you analyze the flight patterns and figure out how to be more efficient when designing UAVs and micro aerial vehicles for military purposes? And this is why I think, like, we're not even, like, you pick a topic and we're not close in terms of where biology is, where evolution is. I think we can do some
But
things.
all that seem to, yeah, if you want to, coming back to where we are in the current scheme of things in AI. So one of the significant shifts that happened, like in terms of at least people thinking of, AI having some level of product level importance,
Hmm.
was when Google acquired DeepMind, and then they came up with their AlphaGo systems. Could you speak about how how was the evolution in machine learning and AI was at that point in time, and how it was developing a more nascent field of machine learning?
Yeah, so AlphaGo and I guess work that led up to AlphaGo. We had, for example, Deep Blue, that beat Gary Kasparov, and Go as a game is far, far more complex than chess, actually. It looks simpler, but there's so many different combinations that you have to explore, and it becomes, far less useful to explore all those options. Meaning, don't even try to explore all those options because it's billion type of type of a deal, right? So it's you can't really explore all those options before making your next move. There's not enough time in the world to do that, and you will not beat your opponent. So what AlphaGo made as progress to this field is, you can use deep neural networks and reinforcement learning, and we're seeing reinforcement learning coming back with, application to large language model training and foundation model training with DeepSeek, and we'll talk about that. But that was one of the main like first application of reinforcement learning that was kind of made very public, right? And it's because you're able to reach or surpass human level performance in something that's super complicated. So humans are using not just learned patterns from chess books or Go references or all of that, but it's also the best players in Go and chess really are the ones who know all of this theory, but then they also have an intuition about what the next move is, what the next 12 moves should be, and sometimes you go against what is theoretically correct and you end up winning, right? So these are some moments of genius that you want to replicate in these kind of models. So with Go players, so it's specifically Lee Sedol, it famously AlphaGo defeated Lee Sedol, but I should say it didn't defeat Lee Sedol 5 out of 5 times. I think it was the score was 3-2 or 4-1 or something like that. So it was kind of
Right. Yeah.
equally paced, and which was also great. And one of the moves, and this is highly debated, one of the moves in one of the games was so very creative and unexpected, and no one really thought a machine, quote unquote, could do this. And the debate is, oh, that could be kind of a random exploration, which is, theoretically, it's good to think about it that way also, because a lot of the algorithms that we see today are a mix of exploration and exploitation, and totally possible. You can't really go back to the logs and check out what happened, but finally it did win, basically laying the groundwork for all of these broader AI applications for long-term decision making and complex problem solving. So it's kind of a proxy for all of these kind of like very complex problems. I do feel though like we're still very happy as a technical community solving the simple problems first. Like these are all very complex. I don't think even the biggest enterprises today are solving problems at the level of AlphaGo, which was 2000, what is it, 2017 or something. So we're still very
Yeah.
happy. Like I said, here's a document. Can you figure out whether this document is signed or not? This is where we are typically. If you average out with broad strokes, across all of these large enterprises.
That's interesting. I mean, yeah, but a lot of the improvement seems to be at more specialized skills and
Right.
something where a lot of expertise is involved rather than more the mundane ones, which is sort of paradoxical to what a lot was promised when the
Right.
real ML and AI trends, started to happen when, a lot of the mundane stuff is going to be automated and we can be a little more creative. But then what seems to be happening is the other way around. A lot of the creative stuff is being taken over. Take the case of, the Hollywood actor strike, technician strike.
Hmm.
Yeah, it's I think we opened the Pandora's box with training these models to become experts than trying to solve the more immediate and the simple tasks. How did we get to this part? I mean, could you explain it? Because what I was thinking also when I was tracking this field is that we are going to have these AI models come and solve those simple tasks, like telling me these are the five different emails that you got, which have been put aside in the junk folder. You don't want to read it, and these are the more important ones. You want to go for it, and these are the list of calls that came from these people. That sort of thing is still not, happening.
Yeah, and I think we're still, there's a lot of different drivers. Let me back up. There's money in certain places. There's kind of grand ideas of AGI, and we're being pulled in different directions. There's you know, in terms of running a product and a business, these simple use cases are the ones that are you can easily adopt at scale and get paid for. And this is where we are in terms of kind of the spread of products. Of course, we see like some golden eggs here and there, but going back to I know we left off, in this journey with RNNs, and RNNs were typically used for time series kind of forecasting. But of course, like a sentence is also kind of a time series if you tag each word by a time step, and each time you increment a time step, let's say you output a word in a sentence, right, until you reach the full stop.
Mm,
And so we started using RNNs for these kind of applications, similar to what you were saying. So read a subject line of an email and then tell me whether it should go to a spam or junk folder, or should it be in my inbox. And we
right.
had all of these initially RNN based architectures, and then in 2017 we had the big transformer architecture, which is attention is all you need. And the audience maybe recognizes this title because it's everywhere. Attention is all you need. We
Yeah.
just had one of our papers accepted, which is called keyword search is all you need. And we'll get to that. But attention, it existed before the attention is all you need paper. I'm not trying to take credit away from the folks at Google, but just for clarity, essentially this attention existed earlier. Distributed training kind of existed earlier. Data processing, tokenization, all of this existed way earlier in kind of language learning literature. But what was kind of interesting is that it kind of replaced RNNs and used a method called self-attention. And a good
Mm,
way to think about that is, if you're, let's say, imagine any sentence and you're in the middle of a sentence, you pick the word. That word has a relationship to the word on its left, the word on its right, but not just that, it also has relationship to the first word,
the context. Yeah.
right? And for example, when it's processing the word it in a sentence, it can look at all of the previous words to figure out what this it refers to, which is useful generally. I mean, if you're just looking at the last, it's called ngrams or the neighbors, you're only hoping that you'll get the context within this neighborhood of this word it, but you don't have to.
Mm,
And so this is why the self-attention is, I mean, it makes sense. A lot of these things actually logically will make sense. We are just waiting for people to, actually put it into implementation, put it out in open source so that the rest of the world can use it. So after this, self-attention, there's also multi-head attention, which means for each one of these, instances of the word it, you can point to different types of relationships, and one head essentially is, one attention head focuses on the word and the context. The other one might focus on syntax, and it learns to do this, right? So this is not a forced learning. This just emerges out of the training, which is what is interesting. We saw, I mean, today attention really we've over indexed on attention is all you need. So everything pretty much is transformer based, which means like language models, any foundation models, video generation, image generation, which earlier used to be diffusion models, but also now it's transformer based or some hybrid transformer diffusion based. Image understanding, video understanding, text, understanding, audio understanding. All of these things have become transformer based. And there's once again a split in the community where maybe Transformers one group says Transformers is the last really big architectural change we you should expect in research, and the other ones are like, no, 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 it's not, that's not true. We have all of these more efficient ones that you can fit more of these parameters in the GPU and be more efficient about learning these foundation models. But this is an ongoing research. Once again, unfortunately, we aren't at the end chapter of the book. We're kind of in the beginning, so we can't peek ahead. But
Right.
there we are.
Yeah, I mean, Transformers was area that I wanted to come to, but good that you actually kind of give a preface to the whole thing. But can you sort of help understand how we kind of navigated from this whole deep mind framework where we were more focused on Arden, and how did we get into this Transformer bandwagon? And it's also kind of generating so much of interest, and a lot more people are kind of jumping onto it. Parts of it you kind of
Yeah,
went through in your preface, but if you could give it in a little more condensed form, I think that will
yeah,
be helpful to the listeners. Yeah.
yeah. So I think DeepMind came at a time where they were playing leapfrog, right? So we saw some older types of architectures, RNNs at the times, and CNNs were around for image-based architectures. And we had kind of, as a community, decided, okay, CNNs are for image-based, workloads, and RNNs are for sequential, text processing or forecasting kind of workloads. But both these kinds of models struggled with, long sequences in the case of RNNs, and in the case of CNNs, they had their own kind of inefficiencies problems. And DeepMind, when they came in and leapfrogged all of this with their really ambitious projects, what they showed is beyond these massive computational resources that you could throw money at and get, right? So these are traditionally, these kind of labs are paid to fail. I mean, it's okay to fail, and then once in 10 projects, if you're really successful, then you're still going to be in business. So in Google's research team, when they introduced, this transformer, it did a lot of things at once, right? So it eliminated these sequential bottlenecks, eliminated what was called the vanishing gradient problem. It could handle very long sequences. It was very adaptable as well. And in terms of, there was also this hardware boom in terms of, GPU hardware and investment there. And so the attention architecture really was highly parallelizable, which means you can make training faster and cheaper effectively, and just more useful for the broader community. And this led to BERT, which is one of the kinds of early model architectures that were based on transformers. And then in 2019, which doesn't seem too long ago,
Too far.
OpenAI came up with GPT-2. And GPT-2, you can still find the exact actual model weights and the thing that they published in the open source on Hugging Face. So you can go there
Right.
and actually download it. I wouldn't expect anyone to go in and actually dig into the weights, even if you could. You will only see a bunch of binaries, but um, that's very interesting. Like that was the base uh, kind of architecture that started it all. And right now we're in a world which is only, let's say 5 years later, where
Yeah,
everything's really taken over, and still
exactly.
transformers are still
And
here to stay, and it's just larger scale than what it was earlier.
how do you explain this thing? I mean, this is something that seems perplexing to a lot of people who Google built this whole transformer. It's like you pointed out, one of their moonshots, like they were paying money for things to fail, but then this transformer seemed to have worked. And then they had the BERT model, and
Mhm.
then GPT is just starting with OpenAI. They're trying to build something, and they're kind of building on top of this, and then they are really topping it up, and then Google is nowhere to be seen once ChatGPT hits on screen. They come up with Bard. Bard kind of, falters
Mhm.
and fails, and then it's kind of given a new name and baptized into Gemini, which is, trying to get into the top of the charts here and there. But how exactly did the shift move from Google to OpenAI, which was like a small kid on the block, right?
Right.
How did that happen?
Also, I mean, the small kernel block with a lot of support and funding, but
Yeah.
I do think like, and I'm noticing this from within Amazon. I'm also obviously, you know, monitoring Azure and Google Cloud, and all of these are major competitors in the AI race, pretty much alongside OpenAI, which has a significant lead essentially. But OpenAI, I think the strategy, I mean, just thinking back now, which is easy. Once everything is done, looking back at history and analyzing the easy thing. But I think they specifically focused on throwing compute and scaling up language models when no one was fully invested in this, right? So they weren't really sold on the idea that this would really make a big impact. Microsoft famously, they had kind of a chatbot out without any guardrails, and that went wrong, right? So you have all of these different signals coming into these different businesses, different kind of incentives, and then OpenAI at the time was going down the open model weights, completely accessible kind of route, even though they had so much investment in it. So essentially, they're at a loss at that point of time. Um, and then I think what happened is that the more kind of compute you throw at this, and of course there's other major things, right? So there's effort spent in curating high quality data, which we still think is kind of the game changer. Anyone who spends time and resources, which essentially mean human resources, curating high quality data and cleaning up everything. We can't just take everything from the web. Turns out those are the folks who are kind of in the lead. But at the time, OpenAI obviously made the decision to commercialize ChatGPT, get more data, and start with GPT-3 and then lead into the APIs and partnering with Microsoft and getting more funding and GPU access, and the rest is history. But I do think like they all of them at the same time. If you look at a snapshot in time where OpenAI was just published GPT-2, they had no funding really. It's just getting interest, and Google kind of is seen as like a research lead for, but really not capitalizing on it. But they have a different business incentive. The core business really wasn't,
Research.
yeah, it wasn't research, wasn't threatened. Like they're traditionally a company who would spend a lot on these moonshot kind of programs. And it's okay, like I said, to fail. Like Waymo is one of those moonshot projects. And I think a lot of these other companies, including Amazon, which I think Amazon is late into the game, honestly. But as like organizational approaches, everyone's different. Like everyone has a different strategy, right? So like
Mhm.
OpenAI is completely closed right now, and forget about hopes of seeing anything into even training details, or because that's their monopoly. Whereas Amazon traditionally as well is on the other end of the spectrum, which is let's provide more choice, let's get more models, let's onboard more partners, and then let customers choose. Similar to Amazon.com. If you're looking for,
Right.
like a, I don't know, phone case, you get 10,000 phone cases. So more choice, cheaper prices, which is the famous like Amazon flywheel. But I should say, Google isn't exactly, you know, kind of behind in the race right now. I think you've seen the latest update on Gemini, the 2 million context window. So that's their strategy. We can question that strategy and
Right.
say who really is going to throw a bunch of books in context to a large language model and ask a question about, one page in the entire book. Seems very inefficient.
Yeah.
And maybe there's some customers for it, but at scale, that's their big bet. And they're obviously funding research and doing more work on kind of proving that you don't need knowledge bases or retrieval augmented generation. In context is a way to go. And in fact, a lot of these organizations, they would have, including Amazon, we have multiple groups of people competing in terms of research objectives. One would say RAG is good, another one would say long context is good. And then folks like us will say, oh, you shouldn't even have a knowledge base. You can just have an agent go through and then do keyword searches similar to what humans do, and you'll still get pretty okay results.
Yeah, and
Um,
keyword is all you need.
yes, that's the title of our paper in like a recent conference called Triple AI. And
I
thanks to,
see.
there's so many dash is all you need after the attention is all you need. And so we're on that bandwagon now.
So on the note, we will conclude the first part of this section on understanding the world pre-OpenAI and the ChatGPT revolution. And then we will go further into how things are shaping up for this industry and making space for much more smaller models to come in. What are the different trends that are emerging since the launch of the ChatGPT models? We will cover that in the coming session. Thanks for taking the time out and listening. Thank you so much, Shreyas, for taking the time and talking through the whole set of, sort of, rich history behind all that's happening in AI and ML. It's been a pleasure having you on the podcast.
Yeah, thanks again for the opportunity. And yeah, until next time, part two.
Thank you for tuning in to the Interface Podcast. For more such episodes on technology and innovation, tune in to the Interface on Spotify, Apple Podcasts, or wherever you get your podcasts from. Do share your comments with us at the interface at thehindu.co.in. To keep yourself updated with the latest tech, please go to thehindu.com or follow us on all social media platforms. Thank you.